material. I think most of us know the details of the work, right? Anuja has read the draft. Danny has. Have you reread the paper?
No.
And
that's what
Joey didn't.
I think at least a few.
Yeah, so two of you actually, you have read the draft, right? Okay.
No. I suggested that you will present this almost like a rehearsal to a conference presentation.
Yeah, the thing is, I want to know the understanding of the audience so that we don't waste time. Or we can even talk about some other issues. For some details, I will skip. Yeah, that's no point.
Better to go through the entire thing without the assumption that everybody understands.
Okay.
Yeah.
Okay, yeah, that's right. So this is the outline of this talk. I'll give an introduction.
Have you changed anything after you sent this?
Very minor changes. Yeah. In the introduction, I'll talk about the fusion aspect in multimedia information retrieval field. How to build the fusion and what does fusion mean in this area. And secondly, we talk about the framework we proposed in that paper. It contains two main parts: automatic query formation and regression model for query dependent fusion. And then we talk about how we evaluated the system and followed by the conclusion. So first, let's talk about the introduction part. In multimedia information retrieval, the documents we are dealing with, of course, are multimedia documents. They are their nature is that they contain normally they contain a lot of modalities. For example, they have text modality, audio, image, and video in general. And nowadays, people in multimedia information retrieval, in different applications, people try to use fusion approach to leverage different modalities or knowledge sources. For example, in web search, the goal is to give it the web search engine a keyword query, and the search engine will utilize different aspects or different modalities of the text document. Well, the text documents does not only have the text modality, they also have some linking information between the documents. That is also another modality. We try to use the two modalities to improve the search results. Multimedia search, of course, we know when we search music, we can use audio content, text, data, and even the video content to improve the search accuracy. Meta search, the concept is to build different search engines. So each search engine returns you a result list. You fuse all those individual result lists and come up with a better one. That's called meta search. So in all these applications, people use multimodal fusion to improve the service quality. And here, normally people in the existing literature, we can categorize the fusion approaches into two categories: query independent fusion and query dependent fusion. Here, query independent fusion is really like no matter the query is, the fusion strategy stays the same within one system. Query dependent fusion means even within one system, we give it different queries. The system will use different fusion strategies. So then in this paper, we propose a new method for query dependent fusion. In the literature, people compared the performance difference between these two approaches. Of course, this more adaptive approach gives better results. Yeah, that's the current observation. This table summarizes all the popular algorithms for query independent fusion, QIF, and query dependent fusion for different query dependent fusions. CQDF means class-based query dependent fusion. Class-based, here we have a single class, and a mixture of classes, mixture. We also have query dependent fusion based on k nearest neighbors, kn. The approach we proposed is called folksonomy regression query dependent fusion. The main idea is that we do not manually design queries. So in this column, we compare how do people form queries in their algorithm. We use an automatic approach to mine knowledge from online social data, for example, the text. We come up with a way to cluster the text into a hierarchy. The hierarchy represents a music knowledge space. In that space, we can automatically form a very large number of queries. Previous approach, people use manual design. Normally, they design hundreds of queries to do their either system training or system evaluation. Here, the automatic way does not involve any human effort, so it's very cheap. And also, it can form a large number of queries, millions of queries, so that we can train the system with a much better generalization performance. That's one aspect in this framework. Another aspect is that we propose a regression model. We all know that classification and regression, they are two very popular approaches in machine learning field. In my sense, they all try to, learn a mapping from input sample into a class, or in the classification approach, or into a value in the regression approach. The difference of their model is that the classification, they have their class structure. Regression doesn't have any underlying structure. It just inherently learn a mapping. So in this case, in this paper, we will talk about the difference of classification-based and class-based and regression-based. We will see the clear advantage of the regression model we propose. And another aspect is that previous approaches about query-dependent fusion, they all tested their performance in either text search, video search, or meta search. In this paper, we have, so far according to our literature review, is the first paper in music search to validate the query-dependent fusion approach. And then we go to the framework. This is a diagram of the system. You can see that it draws the complete flow of a search engine. And in the user side, a user can issue an online query to do a search. You can see there are two parts, the offline part and online part. In the online part, the user just do a search. The search engine will have some underlying search experts. Each expert will return a list, and then we do a fusion of those lists and come up with a final fused result to the user. The paper is really it's mainly about offline approach, which is how do we train or develop the system. First, we'll talk about social query formation. This is the social query space. We form a social query space from online data, so that we can sample queries to train the system and to train our regression model. Another part is the regression model. The regression model, from this picture, you can see its functionality. It takes a user query, it derives a set of fusion weights, which are used to fuse the multiple lists. So from this picture, we know very clearly the functionality of each module and the contribution of this proposed framework. And so next, we'll talk about the social space in detail. The social space, the goal of this module is to automatically form similar queries to the user queries, so that they don't need human efforts to design the queries, but we can have queries which can simulate the user queries to train the system. We need to maintain three properties in order to achieve that goal. The first one is that the social queries must cover a comparable knowledge scope of the user information need in answering user queries, which means the scope of our formed query must have a comparable scope to the answering user queries. And the second one is that it must have a same semantic structure. For example, if the user queries wants to search, I want to find similar music. For example, semantic structure here means the content of the query. For example, I want to find music of classical style played by violin. So the semantic structure is that the music must have classical and violin property. We must